Hello and welcome to lecture 11 of module 2 of this course on accelerator physics. So today we will study about the longitudinal dynamics of beams. That means the dynamics of the beams in the direction of motion of the charged particle, that is in the z direction. So in the previous lectures we studied how we can accelerate the charged particles using time varying electric fields. So we saw that time varying fields can be used to accelerate charged particles to very high energies, and we use the electric fields associated with the electromagnetic wave in a high Q cavity for acceleration. So we saw that we do not apply the voltages directly to the drift tubes for acceleration. We use the electric fields associated with the electromagnetic wave in a cavity for acceleration. So in a cavity, TE, MNP and TM, MNP modes are excited. The indices M, N and P, they describe the field pattern in the cavity. Then we discussed in detail the TM0 and 0 mode in the pillbox cavity, where we have only the EZ field that is constant along the length and the B theta field. This EZ field is varying with time. It is varying sinusoidally with time, and it can be used for acceleration. We can put drift tubes inside the pillbox cavity. In a long pillbox cavity, we can put drift tubes and use that for acceleration as well. And this structure is known as a drift tube linac. In this, the acceleration takes place in the gaps between the drift tubes. Inside the drift tubes, the fields cannot penetrate, and the beam is shielded from the fields inside the drift tubes. We also saw that how a hollow empty waveguide cannot be used for acceleration of charged particles, because there the phase velocity is greater than the velocity of light, and it is not possible to synchronize the velocity of the wave with the phase of the wave with the particle. So it cannot be used, whereas if you load it periodically, you can slow down the wave and then that can be used for acceleration of charged particles. Having studied the various methods of acceleration using time varying fields, we studied about the transverse dynamics of particles. So that is the dynamics of the particles in the direction transverse to the direction of motion of the charged particles. We saw that the beam tends to diverge in the direction transverse to the direction of motion due to various reasons. So the beam has to be focused, it has to be brought back to the axis, otherwise the beam can get lost. So beam can be focused in the transverse direction using magnetic or electric quadrupoles. We also saw that we can use solenoids for focusing. Now then we saw that the force due to the beam self-charge, this is known as space charge forces. The Coulomb effects in linacs, they are usually most important in non-relativistic beam at low velocities, because for relativistic beams, the self-magnetic forces increase and produce partial cancellation of the electric Coulomb forces. So having studied all this, now let us see the behavior of the beam in the longitudinal direction. We know that in the longitudinal direction, the electric field is applied for acceleration, and the electric field has a sinusoidal variation as shown in this figure. So since the field is varying in time, this gives rise to the concept of phase. So depending on the phase of the electric field, the value of the electric field is different. So in a linac, the convention is that we choose this phase as 0. So where the electric field is maximum, this phase is taken as 0. And so the particle seeing this phase will get maximum energy gain, whereas the particle seeing a phase of minus pi by 2 or pi by 2 will get no energy gain, because here the EZ field is 0. So here let's say the phase of the synchronous particle is phi s. The synchronous particle is the ideal particle in the linac for which the linac is designed. So it moves from one gap to the other in the right time and sees the right value of the field in the next gap. So this is called the synchronous particle, and let's denote the phase of the synchronous particle by this green dot. So we have a synchronous particle here. Now let's consider the phase of the synchronous particle lying between minus pi by 2 and 0. So we see here that the electric field is rising with time. Not all particles are the synchronous particle. There will be other particles in the bunch as well. So let's consider two particles. One is the early particle and another one is the late particle. So the early particle is the particle that arrives before the synchronous particle, and the late particle is one that arrives later than the synchronous particle. So this is the time or the phase axis. So the gray particle is the early particle and the orange particle is the late particle. Now the early particle arrives before the synchronous particle, and it sees a value of the electric field lower than the synchronous particle. So it gets lesser energy gain, it moves slower, and in the next cycle it reaches later than the synchronous particle. So you can see here the synchronous particle reaches at exactly the right phase, but here the early particle has now become the late particle. Similarly, the late particle sees a field which is higher than the synchronous particle. It gets more energy gain as compared to the synchronous particle, moves faster, and in the next gap it reaches faster than the synchronous particle. So you see here that it has become the early particle in the next cycle. So you can see that the early and the late particle oscillate about the synchronous particle. So if you go from one gap, now this gap, to the next gap, the particles will again oscillate about the synchronous particle. So when the synchronous particle sees an electric field that is rising with time, so this electric field is rising with time, that is when the synchronous phase lies between minus pi by 2 and 0, the early and late particles oscillate about the synchronous particle and the bunch size is conserved. Now let's see what happens when the synchronous phase lies between 0 and pi by 2. So now we have the synchronous particle, this green particle, lying between 0 and pi by 2. Here the field is falling with time. So we have an early particle here again. Now the early particle comes before the synchronous particle, and since the electric field is falling with time, it sees a value of the electric field that is higher than the synchronous particle. So it gets more energy gain as compared to the synchronous particle, moves faster, and in the next gap it reaches even faster. So it is even earlier. The late particle sees a field which is less than the synchronous particle, moves slower, and it reaches slower, and in the next cycle it reaches even slower. So we see that if we choose the synchronous phase to lie between 0 and pi by 2, then in that case the bunch starts spreading. The synchronous particle will always come to the gap at the right time, but the particles about the synchronous particle, they will keep moving away from the synchronous particle as the beam moves from one gap to the next. So when the synchronous particle sees an electric field that is falling with time, that is phi s lying between 0 and pi by 2, the early and late particles move away from the synchronous particle and the bunch expands. So in other words, there is no phase stability. So for acceleration with phase stability, the synchronous phase must be chosen to lie between minus pi by 2 and 0. So even though the entire positive cycle can provide acceleration, for acceleration with phase stability, we should choose the synchronous phase to lie between 0 and minus pi by 2. Now, having chosen the phase of the synchronous particle to lie between 0 and minus pi by 2, we design the linac. So we choose a phi s which lies between minus pi by 2 and 0, and we design the linac. So linac is designed for the synchronous particle. The synchronous particle always arrives at each gap at the correct phase. Okay, so let's say this is the nth gap. So it moves from here to here in the correct time. So depending on whether it's a 0 mode structure or a pi mode structure, it will take time t or t by 2 to travel from the n minus 1th gap to the nth gap. Okay, so it always arrives at each gap at the correct phase and sees the correct value of the accelerating field for which it has been designed. So let's say we have a particle which is a synchronous particle. The phase of the synchronous particle in the nth cell is denoted by phi subscript Sn. The velocity of the synchronous particle in the nth cell is beta Sn. So here this particle has a phase phi Sn. So in other words, when it arrives at the center of the gap, the field that it sees corresponds to a phase of phi Sn. It gains energy here and then moves from the center of this gap to the center of next gap with a velocity beta Sn. And the energy of the synchronous particle here is Wsn. Now the cell length is given by, so the cell length is this length from the center of one gap to the center of next gap. So here it is Lsn minus 1 into 2. So 2 times Lsn minus 1 is equal to, so this will be equal to beta lambda by 2 if it is a pi mode structure, and it will be equal to beta lambda if it is a 0 mode structure. So we write it as n beta Sn minus 1 lambda, where n is equal to half for a pi mode structure and is equal to 1 for a 0 mode structure. Now we also define a length Ln, capital Ln, from the center of one drift tube to the center of next drift tube. So this is given as Lsn minus 1 plus Lsn. Now a bunch consists of many particles, and not all particles are the synchronous particles. And we've seen that if we choose the synchronous phase to lie between minus pi by 2 and 0, then the other particles will oscillate about the synchronous particle. Now we would like to calculate what is the difference in phase between the synchronous particle and some arbitrary particle that the bunch still remains stable. Okay. So we investigate the motion of particles with phases and energies that deviate from the synchronous value. So we will try to see that what is the extent of deviation in phase that can be tolerated without the bunch getting lost or bunch remaining stable. So the phase of the synchronous particle in the nth cell as before is phi Sn. The velocity of the synchronous particle in the nth cell is beta Sn, and energy of the synchronous particle is in the nth cell is Wsn. Now we talk of some other particle which is not the synchronous particle. So let the phase of that particle in the nth cell be phi n. The velocity of the arbitrary particle be beta n. So it will see a different, since the phase is different, it will see a different value of the electric field, and the energy gain will be different. So the velocity of that arbitrary particle will be different. The energy of the arbitrary particle in the nth cell is Wn. Again, Wn will be different from Wsn. The linac is designed for the synchronous particle. So the lengths will still be according to the motion of the synchronous particle. Now we assume, in order to understand the stability of the non-synchronous particle, we make some assumptions. We assume that the synchronous particle always arrives at each succeeding gap at the correct phase. And we consider particles with velocities that are close enough to the synchronous velocity so that all the particles have about the same transit time factor. Okay, so we assume that the velocities of the other particle are not too far off from that of the synchronous particle. Now we consider the particle motion through each cell to consist of drift spaces plus thin gaps. So this is the drift space, this is the thin gap, again this is the drift space. So we assume that all the energy gain happens in the thin gap in this region, and this remaining region is the drift space. In the thin gaps, the forces are applied as impulses. So instead of the force being applied at the entire gap, which has some finite width, we assume that the forces are applied as impulses at the center of the gap. From n minus 1 gap to n gap, the particle has constant velocity beta n minus 1. So from here to here, the particle moves with a constant velocity of beta n minus 1. Now we will try to write the longitudinal equation of motion of the particles in terms of phi n and wn. So phi n and wn are the phase and energy of the arbitrary particle. Now the RF phase changes as the particle advances from one gap to the next according to, so phi n is equal to phi n minus 1 plus omega t. So here we can write phi n is equal to phi n minus 1. So phi n is the phase of the arbitrary particle in the nth cell. This is the phase in the n minus 1th cell. And to that we add omega t. And t is the time taken for the particle to travel, for that arbitrary particle to travel from the n minus 1th cell to the nth cell. So that is equal to the distance divided by its velocity. So distance is fixed. So distance is 2 times this ls n minus 1 and the velocity is beta n minus 1 into c. And we can add a factor of pi or 0 depending on whether it's a pi mode or a 0 mode. Now we define the cell length. We have already defined this. The ls n minus 1 is equal to n beta s n minus 1 lambda by 2, where n is equal to half for pi mode and 1 for 0 mode. Also the cell length measured from center of one drift tube to the center of another drift tube can be written as lsn minus 1 plus lsn. And then we can put in the values of lsn minus 1 and lsn. So now we want to calculate the change in phase of an arbitrary particle as it travels from the n minus 1th gap to the nth gap with respect to the synchronous particle. So we can write that as delta phi minus phi s n. So this is the change in phase of an arbitrary particle as it is moving from the n minus 1th gap to the nth gap. So how much is the change in phase of that particle as it reaches this gap with respect to the synchronous particle? So this becomes equal to delta phi n and delta phi s n. So let's evaluate the two terms separately. So delta phi n is simply delta phi n minus 1. And this we have already seen from equation 1 is equal to omega into t. So omega into t is the distance traveled by the velocity. So this we can put in the values of ls n minus 1. We get this is equal to n beta s n minus 1 lambda by 2. So simplifying this further, we get this as equal to 2 pi n beta s n minus 1 by beta n minus 1. Now the second term we can again simplify this. So here this is phi s n minus phi s n minus 1. So this is again you can write it as omega into t. So this is the distance traveled by the velocity. So this comes out to be equal to 2 pi n. So this is for the synchronous particle. So the synchronous particle travels at the right time. So it takes either time t or t by 2 depending on whether it's a 0 mode structure or a pi mode structure and reaches here in the correct time to see the same phase. So delta phi s n is equal to 2 pi n. So delta phi minus phi s into n is equal to, we can substitute the values here, phi n minus 1. So phi n is this and phi n minus 1 is this. So we put in the values here and this is what we get. So we can take beta s n minus 1 common here and we get 1 upon beta n minus 1 minus 1 upon beta s n minus 1. Now we can evaluate this quantity in the brackets. So 1 upon, using Taylor expansion, we can write 1 upon beta minus 1 upon beta s is equal to 1 upon beta s plus delta b. Now the other particle does not have a velocity which is too much off from the synchronous particle. So we can just add a small quantity delta beta to the synchronous velocity. So this minus 1 upon beta s. Now for delta beta much smaller than 1, we can write this as delta beta by beta s square, and this quantity we can substitute in the expression for delta phi minus phi s n, the bracketed term here. So we write this as delta beta n minus 1 beta s n minus 1 square with a minus sign. On simplifying this further, we get minus 2 pi n delta beta n minus 1 upon beta s n minus 1. Now we can evaluate this delta beta n minus 1 in terms of energy. So this is, the energy is given as gamma MOC square, where gamma is the relativistic gamma. This can be written in terms of beta as, so gamma is 1 upon under root 1 minus beta square. So you can write this like this. So delta W by delta beta is given as beta gamma cube MOC square. So from here we can write delta beta is equal to delta W by MOC square gamma S cube beta S. So we can put in the value of delta beta n minus 1 here. So this is what we get. So this is the expression for change in the phase of an arbitrary particle as it moves from the n minus 1th gap to the nth gap with respect to the synchronous particle. So here we can write delta W n minus 1 as, so this is the change in energy of the particle with respect to the energy of the synchronous particle. So this can be written as Wn minus 1 minus Ws n minus 1. So this is the difference equation relating the change in relative phase of the particle with respect to the synchronous particle as it travels from n minus 1th gap to the nth gap. Now similarly we can write the difference equation for energy change as the particle travels from the n minus 1th gap to the n gap with respect to the synchronous particle. So this is, we can write this as delta W minus Ws as it travels from the n minus 1th gap to the nth gap. So this can be written as delta Wn minus delta Wsn. So putting in the values of delta Wn and delta Wsn, this is simply QE0T capital Ln, because this is the electric field averaged over the entire cell length starting from the center of one drift tube to the center of next drift tube. Cos phi n minus cos phi Sn. So because the arbitrary particle sees a phase phi n and the synchronous particle sees a phase phi Sn. Now equations 5 and 6, they form two coupled difference equations. So these are difference equations for relative phase and energy change, and these can be solved numerically for the motion of any particle. So these are the two difference equations. This is for phase and this is for energy. So we can convert these difference equations into differential equation. So we can write delta phi minus phi s n as d phi minus phi s dn and delta w minus ws n as dw minus ds dn. Okay, so n is now treated as a continuous variable. So n was earlier discrete. Now when we want to convert this into a differential equation, we can convert this into a continuous variable in s. So we can change the variable from n to the actual distance s. So n can be written as s by the cell length. So n beta s lambda, or half of cell length. So from here dn is equal to ds by n beta s lambda. So we can substitute this in equation 5 and we get n beta s lambda d by ds of phi minus phi s is equal to minus 2 pi n w minus ws moc square gamma s cube beta s cube. So which can be further simplified into this expression. Similarly, the expression 6 for energy can, so this difference equation 6 can be simplified and converted into a differential equation of the form this. So here it is dw minus ws by ds is equal to QE0T cos phi minus cos phi s. So here are the two equations. Now we have two differential equations. Now we can differentiate this expression and we will get d by ds of w minus ws, which we can put in here, and we get this expression. So this can be further simplified to write this expression. So we see that this equation in phi and w, this is a non-linear second order differential equation for phase motion. So from energy and phase, we have converted into a single second order differential equation for phase, and so we see that this is a non-linear second order differential equation for phase motion. Now phase is proportional to time, so more negative the phase, so this is 0, so more negative the phase, the earlier the particle arrival time with respect to relative to the crest of the wave. So the early particle is more negative with respect to the phase at the crest. Also, the phase difference between the particle and the synchronous particle is proportional to the spatial separation. So these particles are the particles in a bunch. Now the bunch in S can be written as can be shown like this. So we have a synchronous particle, and we have an early particle which is here, and late particle which is here. So this is showing the bunch in space. Now if the same bunch is to be shown in time, so the early particle arrives earlier in time and the late particle arrives later in time as compared to the synchronous particle. Hence, if you see the expression for the bunch length and the bunch phase, so there is a negative sign involved. So the phase difference between the particle and the synchronous particle, this is proportional to the spatial separation with a negative sign. Now assuming that the acceleration rate is small, so that means that we can take E0t phi s as constant also, and since acceleration rate is small, beta s, gamma s are constant. So we introduce the following notation. We write small w is equal to w minus ws and divided by MOC square. Then we define A and B, which are constants. So A is 2 pi by beta s cube gamma s cube lambda, and B is q E0t by MOC square. Now these are the two differential equations. Now using this notation where we have defined small w and constants A and B, these equations can be written as, so w prime can be written as b times cos phi minus cos phi s. Similarly, phi prime from here can be written as minus aw. We can differentiate this expression again to get phi double prime is equal to minus ab cos phi minus cos phi s, and this expression can then be written as d phi prime, and we take ds on the right hand side is equal to, so d phi prime is equal to minus ab cos phi minus cos phi s ds. Now ds is d phi by phi prime. So ds is d phi by phi prime. So we can substitute ds as d phi by d phi prime, and we have a d phi prime here, and then we can integrate this expression, and this is what we get. Phi prime square by 2 is equal to minus ab sin phi minus phi cos phi s is plus some constant term. Now this we can write it as, now since phi prime is equal to minus aw, so we can write this as aw square by 2 plus b, so dividing the whole thing by a, so we get plus b sin phi minus phi cos phi s is equal to some constant which we call as h phi. Now if you look at this expression looks like there is a kinetic energy term and there is a potential energy term, and this is like a Hamiltonian which is constant. So the first term is of the form of a kinetic energy and the second term is of the form of a potential energy, and h phi is the constant of motion. So let us try to understand this expression.